Okay, let me record as well. Okay, welcome to this 5-day course. My name is Steven Low. I'm a professor at Caltech in California and also an honorary professor at the University of Melbourne in Australia. The audience is very diverse and the course is designed accordingly. So it will encompass both basic theory and also actual applications in practice. The theory hopefully will provide some structure and clarity for us, help us understand some of the issues that we are facing in decarbonizing today's grid. But theory is necessarily a very simple approximation of the reality. And therefore, when we think about actual applications, there are a lot of challenges that must be overcome. And the course try to cover both sides. And hopefully everyone will find some part of the course useful. So let me start and share my content. Okay, great. Share screen. Stop. Okay, so before jumping into day one's material, let me just comment on the course is on advanced modeling of DER-rich active distribution networks. So the keywords are DER, active and distribution networks. And by DER, we mean very broadly, PVs, EVs, storage, smart buildings, smart appliances, smart inverters, power electronics, and so on. So these are resources some may generate and some are controllable loads. By active, we mean that these DERs, say distributed energy resources, will introduce more and more uncertainty, both in, oh, let me make sure. So it's cut off a little bit. Let me see. So I don't know why it's cut off a little bit. Feedback, it might be okay. Okay, let's see. Okay, this is the bits that are cut off now are not that important. So let's continue to see what happens. So they will introduce more and more uncertainty, both in generation, but also in demand. And they are ubiquitous and large scale. And the implication with this is that the control paradigm for distributed systems of the future is that it needs to be distributed real-time feedback. So somehow, why is it? Oh, I lost connection.
Yeah, we lost your presentation, Steve.
Yeah, I don't know why. So let me, oh, my iPad Zoom stops. So let me join again. Sorry for the technical difficulty. Let me join again.
Recording in progress.
Okay, great. Oh, Arthur,
I can hear you. Now I cannot. Now you are muted.
Recording in progress.
Okay, good.
I need to disconnect my audio. Okay, now it's fine. Screen. Start broadcast. Okay, great. So this sharing is actually better than before. So the feedback control and optimization, if there's no uncertainty, then feedback, real-time feedback is not important because we can forecast exactly everything and then we can pre-plan all our control actions. As uncertainty increases, real-time feedback becomes more and more important. And it's a distributed system, and two of the characteristics of distributed system, among many others, is that it is radial, so it has a tree topology, and also it is unbalanced three-phase system. And these two features, it turns out, have important computational implications that we'll see in day 1 and 2, and also other days of the week as well. And the second thing, as I mentioned earlier, is that the course will cover both some basic mathematical theory underlying the distribution system modeling and also real applications. So for example, optimal power flow is very important because it underlies numerous power system applications and planning. So we will look at, for example, some of the empirical experiences in solving OPF and also the underlying mathematics, trying to understand what we see in practice. We'll look at some relaxations. This is an approach to solving OPF and also some analytical properties of these relaxations. We'll also cover stochastic OPF and reserves on Thursday. And tomorrow, we'll look at some real applications, including DRs and three-phase OPF in actual medium voltage and low voltage networks. And on Friday, we will look at multi-energy flexibility and grid services. Okay, so let's jump right into day 1. Day 1 will cover some basic mathematical theory for general networks. And then in day 2, we'll look at some similar theories, particularly for distribution networks that have radial topology. So for today, there are roughly 4 blocks, and each block is roughly an hour, but not exactly an hour. Some may be 5-10 minutes over, some may be 5-10 minutes less. So I'll try to manage the time so that we can squeeze all these materials within the 4 hour, including breaks. So the first block will cover the basic, is a review, hopefully for most of you, if not all, of power flow models and the solution methods. We'll cover AC power flow, DC power flow very, very briefly, just so that we have all the notations down and we're on the same page, and the basic computational methods. So the green piece, there are nodes on Canvas, if you can access them, and this refers to the sections in the nodes, the chapter 7.1 and 7.2. The second block talks about OPF. We formulate OPF as quadratic constraint, quadratic program, and semi-definite relaxations of these QCQPs. And then we look at how the different relaxations might be related. And in particular, when we have a tree topology, some of those relaxations are equivalent. And the third block examines some empirical experience with OPF. OPF has been proved to be NP hard, so computationally is hard in theory. In practice, it seems to be easy in that if you run relaxations, typically the relaxations are exact and you get a global solution. If you just run local algorithms, such as gradient algorithm, Newton-Raphson, for example, where typically it turns out you will get a global optimum. And this is quite, is a great news. And we want to understand not only empirically, but also what are the underlying mathematical structure of the problem that gives rise to this empirical experience. So in particular, we'll look at some sufficient conditions that will guarantee exact relaxation of OPF, and also conditions, sufficient and necessary conditions when we have both exact relaxation and no spurious local optimal. That is, if you run local algorithm, you will get a global optimal. And the last block looked at very briefly some extensions, and there are 2 main topics. One is the models, OPF relaxations will, and also those analytical properties, turns out can all be extended to unbalanced 3-phase system. And then the second topic is another convex relaxation proposed by Pascal van Tenryck, actually while he was in Australia, associated with Melbourne University and NICTA. So hopefully we will have time to cover all of them. The day 2 will cover a set of models that can be applied to general networks, but are particularly convenient for radio networks. And it turns out this set of models, what we call branch flow models also are numerically much more stable when we try to solve OPF at scale. So day one, we do have some simulation. We'll cover some simulations and talk about very briefly some applications in day one, but mostly is mathematical theory. Day two, therefore, I will start with application. So I would describe a real application of distributed energy resources optimization. This is a project that we did several years ago with local utility company, Southern California Edison. So I describe the application, describe some of the simulation results. Hopefully that motivates why do we care about understanding some of the underlying mathematical structure. And then I will talk about branch flow model, which is another class of power flow models. And in what sense is this set of models equivalent to the models that we cover in day one? And one nice thing with radio network is that you can compute power flow solutions extremely efficiently using this backward forward sweep method. And that's useful in not only solving power flow solutions, but also in OPF. So we use that in the applications that I talked about at the beginning of day two, DER optimization. So I described what backward forward sweep algorithm is. Another nice thing with the branch flow model is that it has a linearized model that is much more suitable for distribution systems than DC power flow model. It has very nice, not only better model, but also it has a very nice analytical properties. So I will talk about that and also using that and describe an application in distributed control for voltages in distribution systems. And then I will talk about, so the first two talk about just power flow models, include the linearized model. And then the next block will talk about using this model to formulate OPF, the resulting semi-definite relaxations. And then I'll go through in detail a two-bus example. And Carmen, who's also on the audience, a co-host and a PhD student at University of Melbourne, will describe in detail how you can use codes to really look at quantitatively the structure of this two-bus system that illustrates how, for example, the load in the system will affect the solvability of the power flow solutions and also SOCP and its exactness. Finally, I will describe how to generalize all of the above, both the models, the linearized model and its analytical properties, and also the relaxations from single-phase system to unbalanced three-phase system. Okay, so that's that. If I see some questions, should so maybe unless Carmen and Arthur ask me to stop and answer those questions, for now I will just ignore them and then go into the.
So since you stopped, Steven, they have a question regarding. Appreciate definitions. Question for later. What is an acceptable interval for real-time feedback? Is it sub-second, minutes, or 5 minutes?
It would depend on applications. So for example, I guess in transmission system, 5 minutes is very much real time. Some markets will have 15 minutes, but minutes is real time. For some newer applications, and also another example that we looked at is in the control of, say, EV and HVAC. We also control at the timescales of minutes, say 5 minutes, so on. In actual EV charging system that we develop as well. But in some other applications, we might be looking at seconds. So for example, if we do frequency regulations, either on the low side or maybe even on the general certainly on the transmission side, traditionally, then the primary and secondary control will be seconds, primary control. So on the low side, there are markers that have this regulation D where ISO will send controllable loads, for example, or generations. I guess if you can shed loads and so on, every few seconds, 2 to 4 seconds. So it will depend on the applications. Any other question I should answer?
No, that's all. Thanks.
Steven, just to,
Yeah.
I suggest that unless the questions are really essential in terms of there's something is not clear from the lecture or that, probably we can just keep these general questions for the 30 minutes break. You may want to have a look at these questions during the 30 minutes break, because otherwise I suspect it would be too much distractions. You know, we have like hundreds of people attending. Again, unless the questions are really essential for the lecture, probably something you can look at later.
Yeah, it's a great idea. Thank you. Yes. Okay, so let's get started on the AC model. So I will go through this very quickly because supposedly this will be review, but I want to make sure that we are all on the same page, at least on the notation. So AC models. So a general model is to think of different devices in the network can be modeled as two types. One is a line. These could be transformers, transmission lines, and so on. That's characterized, that joins two nodes, J and K. And the line is characterized by 3 parameters. YJKS, which is a series admittance, is a complex number. YJKM, which is the admittance from at JN of the line JK, and YKJM, that's the shunt admittance on the KN. And then the variables typically we looked at are nodal variables. There's small sj, which will be real and reactive power and power injection and node J. IJ, capital IJ, which is the current injection from node from node J to the rest of the network, and then the voltage phase of VJ. So all numbers are complex numbers. So that's the pi model here, where you can think of where all these parameters are, the 3 parameters, but it's also 3 nodal variables. And the current is related, the injection at node I is simply the sum of current IJK from J to K. So notice from the current from J to K, IJK is different from the current from K to J, IKJ, because of the shunt element. And they satisfy these powerful equations. So this is the complex form powerful equations. And you can write this in terms of the admittance matrix in a vector form, where I is the vector of capital IJ, subscript J's. V is the vector of voltage phases on the entire network, and Y is this admittance matrix. So we assume there are n+1, capital n+1 nodes. So node 0 is the slack bus or reference node. So Y is a complex matrix in n+1 times n+1. So important property of this admittance matrix is that it's symmetric, it's complex symmetric, but it's not Hermitian. And that's where a lot of the computational issues arise. But it does have some property with being a complex symmetric. And some of these properties are in the lecture notes. So the power injection Sj is related to the line flow, power on line from J to K by, this is simply power balance, and Sjk is Vj times the Ijk star. And if you write this out, this will look like summation K to J, Yjks. I use H for Hermitian product is a matrix, but H for a scalar is also just a complex conjugate. Vj square Vj Vk star plus so Yjkm H square. And therefore, we see that the there's a sum. So sorry. So there's a sum here. Let me. Oh yeah. Okay. All right. So we see that the power flow equation is quadratic in the voltage phase of V, and that's where a lot of the that's where the non-convexity comes in. So this is the complex form. So we call this, let's just call this power flow equations, but in complex form. There are at least 3 forms. You can also write power flow equation in polar form, where you simply look at the variables are not the complex numbers, but the magnitude, the phase of the complex voltage phasor, and also so instead of writing Sj now becomes the real power injection and reactive power injection. So these are the variables. And therefore, you can just convert the complex form into this. And it looks like this, Pj. So let me just use the generic Gjk Vj square cosine theta jk minus bjk. Okay, so let me make a few notes. One is that I use the notation where the yjk, whether it's the series admittance or shunt admittance, to be gjk minus bjk, so that in generally, let's say for transmission networks, then both DJK are positive or non-negative. So some authors use bjk to be negative, and then you have gjk, the bjk to be negative, so that then you have y equals g plus b. So I use minus b. The second thing is that the theta jk is theta j minus theta k. Okay, so it's pretty standard. And qj equals vj vk okay, so you just convert from the complex form to the polar form. It's the same thing. Or if you instead do this another conversion where the variables are Vj, instead of writing it in the polar form, you can write it as real and reactive, real and imaginary part. Then again, if you just substitute Vj equals Ej plus Ifj and equate the real and the imaginary part, then the complex form will produce the following thing that looks like Pj Gjk E square F square minus Ej Ek minus EJFK. and QJ BJK. Minus BJK, EJEK, FJFK, minus FJEK, EJFK. So, and then the different types of buses, PV bus, PQ bus, slack bus, and so on. And what that means is that it's the following. At each node, or bus J, so I'll use node and bus interchangeably. There are 4 real variables. So there's a injection PJ, QJ, and there are magnitude of the voltage phasor and its angle. We have n+1 quadratic equations come in complex form, and therefore in real there are 2 n+1 equations, and there are total 4 n+1 variables, and therefore given any 2 n+1 variables, if they are given as parameters, then we will have 2 n+1 variables, remaining variables, and 2 n+1 equations. At least the number of equations and number of variables match. Because it's nonlinear, it does not guarantee there's a solution. And if there's a solution, it will be unique. But at least we will have same number of equations and variables. And therefore, at each bus, you can specify any 2 of the 4 variables. If you specify, for example, the PQ, that is called a PQ bus, that typically represents a low bus, and you would determine its voltage phasor. So that's a power flow problem. Now in optimization, like OPF, then you specify typically fewer than 2 n+1 variables, and therefore you have more variables than equations. And you want to choose power flow equations, that is to choose 2 n+1 variables among those more than 2 n+1 variables, one that will minimize the student costs, right? So that's the optimization. So, okay, so that's the AC, DC. Okay, so DC model makes a few assumptions, which are reasonable assumptions for transmission networks, but typically not for distribution networks. One is that it's lossless. The lines are lossless, approximately lossless, which means that the loss is very, very small compared with, for example, the power flows on the line. And the implication of that is that the GJK is 0, and therefore our admittance for the line, series admittance for the line, is simply BJK. And also there's no shunt element. So that's the assumption for lossless. The second assumption is that the phase angle difference, theta J minus theta K, is small. So this is small voltage angle difference. And the implication of that is that in the polar form of our power flow equation, we can approximate sign by replace this by theta J minus theta K for all lines. We assume the all voltage magnitudes are fixed and given. Right? So the justification for many applications, transmission network applications, is that the voltages are controlled at a much faster time scale. And therefore, for many applications that we care about that involve power flows, then we can assume the voltage is control well and at its nominal value, or very close to its nominal value, so that we assume it's fixed and given. And then we ignore all reactive power. Okay. As a result, if we make these assumptions in the polar form power flow equations that we saw earlier, then we get the linear power flow equation that involve only the real power, Pj, and theta j, right? So the other two variables, which are the reactive power Qj, so we ignore that, and also the Vj magnitude, which are constant. And therefore, the only DC power flow, the variables are Pj and theta j, and it is this Vjk, Vj, Vk, which are constant, times theta j minus theta k. Right? So this is a constant. So let's call this Bjk tilde. And therefore, this is a linear equation. And in vector form, which is very convenient, is can be written in terms of the instance matrix. So this is, let me use C bar to include, this is n plus 1, the number of nodes by the number of lines by, let me just call this m. M is the number of lines in the network. So the matrix is defined by, from node J and line L, right? L is some ik, for example. So this is 1 if the line is of the form from J to K. So the note, in instance matrix, we think of the network as a directed graph with arbitrary orientations. You fix orientation, then on every line, we write JK in the set of edges lines, or we write J to K to indicate, to emphasize that it's a directed line. Okay. Now, okay. So it's 1 if J is the outgoing node for line L, is -1 if J is the incoming edge, node of the edge, and then 0 otherwise. Okay. So this is a standard instance matrix of a graph, and in terms of this matrix, then this can be written in compactly as, so P bar, I use a bar to denote P0, P1, Pn plus 1. And the reason is that for many applications, we will only compute P1 to, also Pn, sorry. So this is Pn, so n plus 1 of them. We will compute only P1 to Pn and ignore P0, and therefore P bar, sometimes we use P without the bar to indicate the vector, the n dimensional vector. Okay, so then, so this equation becomes C bar of capital P. Capital P is the vector of line flows, capital P JK. And capital B is B, which is, let me write this first, and then theta. Okay, so B is the diagonal of B. Let me use line. So I will indicate, okay, tilde, and B capital M tilde. So that's a diagonal matrix of subsectences on the lines. Cancel that. Oops. Okay. Okay, so let me see, what time is it now? Okay, so I'm okay. Let me just make a comment on how this is used, since I think I still have some time. Okay, so this is the DC power flow equation in vector form. We can eliminate the line flows and obtain P equals this transpose of theta, right? If we substitute the line flow into this, you just get this. But this matrix is a very important matrix. It's called Laplacian matrix. It has many nice properties and a lot understood about Laplacian matrix. And therefore, for example, from that, let's see, we can solve the theta to be the pseudo inverse of the Laplacian matrix times the injection. So given the injection, so what does this mean? It means that if we know the injections, then we can compute what the theta is, the voltage angles. So the vector, right? Just through the pseudo inverse of the Laplacian matrix. And also the line flow. So this will be the vector of P1 to Pm. So the line flow real power line flow vector can also be expressed in terms of the injection. And therefore, given power injections in DC model, we can explicitly write down the angles in the network and also the line flows on the network. Okay, so the Laplacian matrix is n+1 by n+1, but you only assuming the network is connected, then it only has rank n, which means it's not invertible, but is only the null space is only the span of the vector 1. And the implication of that is that the theta, the angles on the network, is you need only up to an arbitrary reference angle. And that's what it means. It doesn't matter what the reference angle is, it will not affect the power, the line flows in the network. Right? So DC power flow, even though it's approximation, is very widely used, especially in transmission network. And one example of that, so let me see if we have time. It should be fine. Okay, so let me just write that down to show the one example. One example of that is in what's called economic dispatch or DC power flow. This is the problem of given loads in the network. This is transmission network. We want to schedule generations, the bulk generators, right? And you can formulate this as typically you want to minimize. So this will be the nodes, Fi of Pi, Fi. So Pi is the real power injection. Typically, PIs represent generations. But in the future, it may also include loads, flexible loads. Right? And therefore, generically, we can think of this as a controllable injection Pi at each node I. They can be generation, they can be load, they can be prosumers. If the injection at node I is not controllable, is fixed given load, then we can do this. So let me come back to that point. And you want to minimize the cost, which could be linear, over the injection vector P bar, subject to its capacity constraint, mean and max, right? So if node J is not controllable, so Pj is given, then you can simply, in this formulation, to set, so this is a component, so there's no bar. So Pj is the jth component of the P bar vector. Pj of mean to be Pj of max, to be whatever value that it is specified to be at the Pj, right? And therefore, this model is pretty generic, assuming Pj a variable at every node j, so that the Pj, oh, INJ, okay, so let me use j. So this is j, Pj, Fj, and Pj. Sum equals 0, so this is supply-demand balance. And then we want to include the line flow limit, right? So the line flow limit is, using this, is BCL P bar less than some, this is capital P, line limits, P max, and let's say P minus P max. Because it's direct line, and therefore there's a P max and minus P max. So this is a typical formulation of economic dispatch, or sometimes it's called DC power flow, where you want to schedule generations subject to 2 or 3 sets of constraints. One is the capacity constraint, which is this. One is power balance, and one is the line flow. You can include other constraints as well. They're all linear, and therefore they can be solved easily, linear programming. It also has lots of interesting properties that come from the properties of linear programming, or in general KKT conditions. If the FJs are convex but not linear, then you still have simple convex problem. You can write down the KKT condition and prove many interesting properties about this problem. And this all relies on the DC power flow, the properties of DC power flow models. So interesting properties are such that if you solve this problem, you get a competitive equilibrium. In particular, it means that the optimal pricing of the electricity will come out of this problem. You get the LMP, you can prove properties of LMP, such as that it is incentive compatible. It maximizes the social welfare and also clear the market. You can prove congestion prices, properties about congestion prices, and you can have very interesting interpretation of congestion prices, how that depends on the line capacities, depends on the capacities of the generators, and so on. You can prove, for example, that the merchandising surplus is non-negative. What it means is that the ISO that runs the market will not run cash negative. And in fact, it will be cash neutral if there's no congestion in the network. And therefore, the merchandising surplus is exactly the congestion rent in the network, which you can use to do this financial rights. And all of this can be proved by looking at the KKT conditions of this problem, and they really boils down to properties of DC power flow. Okay, so that's the comment on DC power flow. Let's now look at the computational methods. And for that, I mainly I mean computational method for AC power flow equations, right? Because DC, you can just write down the exact solution given the injection. So we'll look at two. One is Newton-Raphson. One is fast decouple method. Okay. So both use polar form power flow equations that we saw earlier. And we start with the Newton-Raphson. And then if you make certain approximations of the Newton-Raphson, you get a simplified version of Newton-Raphson, and that is fast decoupled methods. And there's a set of fast decoupled methods. You can make further assumptions, some linearization assumptions, and further simplify the computation for fast decoupled methods. And eventually can be connected to the DC power flow equations as well. So what we will do, we won't go into all those details. We'll just look at what is Newton-Raphson and what's the first major set of assumptions or approximations that you make to Newton-Raphson to get the first idea of fast decoupled method. Okay, so the Newton-Raphson algorithm is to solve, in general, some nonlinear equation fx equals 0. So x is in our n, and f takes a vector, n-dimensional vector, and give you a n-dimensional vector. And this is, the idea is really Taylor expansion of the function f, right? Now, how is this connected to solving optimization problem? Well, you can, for, let's say, even for, let's think about a convex problem so that the necessary, first order necessary condition is also sufficient, right? If it's non-linear, then typically you get a local algorithm, hopefully you converge to a local optimum, right? So let's ignore the local versus global issue and just think of, you have a convex, nonlinear convex optimization problem. You can write down the KKT condition, which is a set of nonlinear equations. If it's constrained, then you get the complementary slackness, which typically involves some bilinear forms and so on. So you get a set of KKT conditions, which takes the form of fx equals 0. And therefore, many of the optimization algorithms is simply trying to solve for a KKT point, a vector x star that satisfies the set of nonlinear equations. That's your KKT, right? And therefore, we can think of Newton-Raphson as simply solving a set of nonlinear equations. Okay, so the idea is that if you do this Taylor expansion on f, then you get f of x. So it's iterative. So let me just use xt, right? So, you get an iterative algorithm, which is Newton-Raphson. At each time t, you have a vector x of t, and what you want to do is to decide to move from xt to the next point, xt plus 1, so that is closer to a solution of fx equals 0, hopefully. Right? So how do you compute xt plus 1 is the question. And the idea is that I'm at xt, I look at my f, and I do a Taylor expansion to move from xt to xt plus delta xt. So this delta xt is what I want to determine, because if I know the delta, then I know where my next point is, which is xt plus delta xt. So the expansion is f of xt plus the Jacobian evaluated at xt times the vector delta xt, right? Plus higher order terms. So this is the matrix of the fi, the xj evaluated at xt. So this is this matrix, the Jacobian matrix, okay? And okay, so this matrix, we'll just write dx of x of t. Okay, so now if we ignore the high order term, right, then so that's the first assumption or idea. The second idea is because I'm solving for fx equals 0, and therefore ideally I want my next point evaluate the f evaluate the next point to be 0, right, to be origin. And therefore, this will give us a relationship between delta, which is what I would like to compute, and the other quantities that I know once xt is given. And therefore, this gives us that the matrix, Jacobian matrix, times the variable that we want to solve, which is the vector of delta x at time t, equals minus of f of x of t. Okay. And therefore, if the Jacobian is invertible, then conceptually, not how we actually compute, but conceptually, delta xt is the so let me write directly. Let me write the next point, t plus 1 is xt minus the inverse of the Jacobian matrix times f of xt, right? So this is, again, conceptually how we compute the next point. In actual computation, we typically do not, we try to avoid computing the inverse of a Jacobian. But instead, we solve this linear equation for delta xt, and there are many ways to solve linear equations efficiently and exploiting different properties of the equations. So pictorially, what's going on is that you have a so this is x, and you have a let's say this is f of x. I'm at the point of xt. So what I would do is I approximate my function f by a linear approximation at the point xt and f of xt. So this is yeah, okay, fx, that's oops. Okay, and then the linear approximation at xt will hit the x-axis, and this is my next point. Right, so I move from xt to xt plus 1, and then I repeat. I approximate the function as xt plus 1, draw a linear approximation, and then when that and where it hits the x-axis is the xt plus 2. So that's the general idea of Newton-Raphson. Now, when we apply to the polar form, then the we only apply this for PQ buses, but let me ignore that, assuming all buses are PQ except the reference bus, so that it simplifies the notation. Then what do we have, right? So we have PJ equals that polar form expression, right? So this one, okay. So this is what we use for Newton-Raphson. Now the right-hand side here, we can write this as some nonlinear function, which we're going to call Pj as a function of the theta and v. Okay, so I'm using abusing notation to use Pj to denote both the injection, the real power injection at node j, but also as a function of the vector of phase angle theta and the vector of voltage magnitudes v absolute value. Okay, so and therefore this equation is simply Pj equals Pj function of theta and v, which is a nonlinear equation that we're trying to solve. Okay, and similarly for Q. Okay, and therefore the equation that we try to solve using Newton-Raphson is of the form Pj, which is a scalar, equals Pj as a function of theta mv, and Qj equals the Qj is a function of theta mv, right? So that's a nonlinear equation, and we know how to solve them using Newton-Raphson. So the corresponding f, right? So Newton-Raphson is trying to solve fx equals 0. This corresponding f is a function of theta, and v is the function of theta and v minus the given given number pj, right? So this is in vector form, so I ignore the component. So this is p and p. So this is a vector of p's and vector of q's minus q, right? So that's the function. We want to solve this and for the roots, right? So okay, so and the Newton-Raphson says, at least conceptually, what time is it now? Oh, okay, good. I think my schedule, let me check my schedule. I think my schedule is such that I have, that's right. Oh, yes, okay, good. So I should speed up. So you choose the initial point. Which is some theta at 0, v at 0. And the initial point is important. It determines whether you're guaranteed to converge or not. And there's a theorem that gives you sufficient condition under which you will guarantee to converge to a local optimum. If it's a Convex problem, then it's global. Otherwise, it may not be global optimal. And then you solve for the deltas, delta theta, delta v, from this linear equation. So the Jacobian of theta v times the delta that you want to solve for equals minus f, which is p as a function minus p vector that is given. So it's the gap. You want them to be equal, and whatever the gap is, that's p and q as a function minus the given real and reactive power. And then you set theta v at the next step to be the current plus the delta. Okay, so you just repeat until some stopping criteria is satisfied. So in this step, the difficult and important step is computing the Jacobian. And then once you have the Jacobian, then you have to solve this linear equation. So the fast decouple algorithm is the following observation. Is that if we look at, take a closer look at the Jacobian, right? So the Jacobian, JK, right, which, well, the two plots, there's dp and there's a dq. So let me, just to simplify notation, let me just go directly. The pj, here pj is the function, not just the given scalar, but the function as a function of theta and v. This function, the derivative with respect to theta k, you can write this out. That's the polar form. You take the polar form, and then you take the derivative. It's a simple derivative involving trigonometric functions. Similarly, you do dq dv evaluated at theta and v. So if you write this out, okay, let me write out one expression to illustrate the point. So it will look like this. JK sine BJK cosine. If J is not equal to K. Okay. It turns out you can take the derivative, massage it a little bit, and then it turns out it will be QJ theta V plus sum over I BJI and VJ squared if J equals K. And then similarly for the Q, but let's look at just the P. Okay, so this is a diagonal block. Okay, so the Jacobian theta V has dp d theta, which is a block, dp dv, another block, dq d theta, and dq dv. So these are the diagonal blocks. Okay. And then let's look at the off-diagonal blocks. We do the same thing. We look at the pj dvk, and then the qj d theta k. Okay. So let me write out one expression just to illustrate the point that we will see theta jk g jk cosine theta jk. If j is not equal to k, and pj theta v, which is the function divided by vj plus ji vj. Okay, if j equals to k. Now the key is this, and similarly for the qdj. But let's look at the case when if the theta jk is small, okay, so that we can set sine of theta jk equals 0. And also if it is lines are lossless, so that we can set gjk to 0. Now, if we take these two assumptions and substitute into the diagonal off-diagonal blocks, this becomes 0, this becomes 0, this becomes 0. And in fact, if you substitute this into the function pj, this also becomes 0. So what's the conclusion? The conclusion is that this block, the off-diagonal block, is approximately 0. And we're going to assume it is 0. If you do the same thing for dq d theta, you will conclude that this is approximately 0. And we're going to set it to 0. And therefore, the Jacobian matrix will become decoupled, will be block diagonal. So the approximate Jacobian matrix will have the structure dp d theta, dq dv, and 0 blocks. So that's a block diagonal structure of the Jacobian. Now, again, you can make further approximations and even simplify the dp dp theta block and dq dv block. But at least now you reduce the Jacobian matrix by the size by half. You can solve these sub-block equations. That's much faster than the original Newton-Raphson. Okay, so that's the idea. And I will stop here. Good. There's some other stuff in the notes you can look at. In particular, this Cantaro, let me see if I have that's in the equation. Yeah, there's this Kantorovich theorem that basically gives a sufficient condition that roughly says that if you start close to a local optimal, then the Newton-Raphson will guarantee to converge to a local optimal. Okay, so a little bit. Okay, let me see. So yeah, so we run a little bit over. I will try to catch up later. So let's take 5-minute break. Okay, let me stop the recording. Stop recording. That's that.